All right. Good afternoon, everybody. So, our next graph algorithm that we're going to discuss is breadth first search, and after that, we'll see the all pairs shortest path algos. One of them is Floyd-Warhsall, and the other one is Johnson's. So, let's start with we just go over depth first search once again. So, just a second. Yes. So I just go over this briefly. Um, you have, you know what DFS means. You have to explore all the vertices, starting at the source and going as deep as possible the first time, and then once you reach a dead end, you come back. Okay. So just like in DFS, we use timestamps or we use coloring to denote the nodes that have been visited or not visited, or that have been done with. You use the color white, gray, or black for the same, and we'll do the same in case of depth first search as well. Okay, so this was the algo for DFS. So just added it in this. How we proceed with DFS is by moving to the next one of the first adjacent vertices, and we put a timestamp. You will see the timestamp will be at the most equal to twice the number of vertices, because we take the timestamp as the number of steps we take forward to do a job. So one, I was at U. Two, I'm at V. If I have to return from V, I color it black, so I give it the timestamp at which it was colored black as 3. But here we'll go ahead at time 3 to y, then we'll go to x. From x, you have to actually return back to, you have to color it black. So you put the timestamp 5 when you actually color it black. You come back to y. Y also does not have any adjacent vertex, so you color it black. Then you go back to v, color it black, it has no adjacent vertex. And then you color the initial vertex as black. So DFS, if you remember, there are two actual functions. One is that loop that calls DFS on all vertices if they are white. So once you're done with this path, all the vertices here are black, but there are two more vertices, W and Z. So we will start with the next available vertex in your adjacency list. So W, and you go to Z, and this is B is a back edge. Um, so there is no adjacent vertex, it turns black, and this turns black. So you are visiting every vertex and you are basically traversing every edge at least once. So the total runtime is V plus E for DFS. So we also, if you look at the timestamps here, you see starts at 1 and it ends at 12. So you have, there are 6 vertices in this graph. So at the most, the timestamp, the maximum value of the timestamp is 12. It is twice the number of vertices you have, 6. Also, you will see that the interval of time for example, your U. Here, the interval of time is 1 to 8. All the descendants of U, or all the vertices that you reach through U, by starting at the source U, their intervals will fall within the interval of U. So 2 7 is within 1 8, 3 6 is within 1 8, 4 5 is within 1 8. You'll see 9 12, it's not within this range here. So that means W is not a descendant of U in the final depth first tree. But you'll see 9 to 12, your 10 to 11 falls in between. That's why your Z is is a child, or you can say it is approached through W. So that's what your, there is this parenthesis theorem. It says that if the start and the finish time of your DFS for a particular vertex falls within the start and the finish time of some other vertex, here, for example, here, if this interval lies within this interval, then V is a descendant of U, or this is vice versa. If the time interval of U, the discovery and the finish time, falls within the discovery and the finish time of V, so U is a descendant of V. And if the discovery and finish time of U is less than discovery and finish time of V, or vice versa, here, then they are not descendants of each other. Okay. So if you're just given the timestamps, you will be able to figure out which one is a descendant of which other node. Okay. So if you see at the bottom, this is the parenthesis, or you can say this is how they, how the time interval will, it will be grouped together. So if you're starting at S, okay, you go to Z, then you see S and Z, you're still actually opening up the vertex for further discovery. So that's why you see a open vertex, open parenthesis, then you go to Y, then you go to X. From X, there is no outgoing edge. And just a second. Just give me a second. Okay, so you see the, once you reach X, there is no outgoing edge, so we actually close X or blacken it. So that's why this time interval here, the X is closed, then you go back to Y once you blacken Y. So this basically is the sequence in which your this time discovery and finish time intervals, this is how they'll be grouped together. So this will tell you, or everything is a descendant of S, here everything is a descendant of T. Okay, so this is your, this is your timing for depth first search. For breadth first search, we don't do this timing, but we do, as the name suggests, it's a breadth first search. So you explore all the vertices that are, you can say, within the same reach. So you discover all the vertices which are one step away. Then you discover all the vertices which are two steps away from the original source node. And we don't mark the timestamps, we mark the distance, as in uh, one step away, two step away. So this, it kind of grows into a tree with many edges, many children, depending on how many adjacent nodes are there. So it's like you start at a starting point, you radiate outwards, you reach the vertices at uh, which are adjacent to you, then you go to the vertices that are adjacent to these adjacent vertices. So that will be level 2 and then level 3, and that's how you build your breadth first search tree. Okay, so again here we use the same notation. If you have a white node, white would mean not discovered or not touched yet. If you have just discovered a node, it is gray until you know everything adjacent to it is also turned gray. Once everything adjacent to it turns gray or black, then this will turn black. Okay, so you are again given a graph with vertices and edges. We mark, we don't mark the discovery time, we mark the distance. So distance is measured in terms of the smallest number of edges or the shortest path from your source to a particular vertex. So if a vertex is not reachable, we'll mark the distance as infinity. Then again, we use a predecessor or a parent to store the parent of every node so that we know what is the shortest path in terms of the number of edges from the source to a particular vertex. So before going here, I had a graph somewhere. I think I deleted that. I'll just show you that. I think I deleted that. Okay, let's just have a. So let's say we have a graph. Okay, this is my source. So your first step will be to your source is white. So you will see what are the adjacent vertices of source, and you will put all of them in the queue. So let's name them with numbers. There are 6. So source, you started at source, you put source, there's a queue, you put source in the queue, simple queue, no priority queue. So when you extract S is at the beginning, so distance is 0. Distance for all the others is infinity. Let's just assume that. Once you take out S, you enqueue all the adjacent vertices of S. So now all of them go into the queue. Okay. Now everything is in the queue. As you enqueue all of them in the queue, you set their distance as 1 because they are at the distance is distance of S plus 1. So what is the distance of S? S is the source node. The distance to source node is 0. So everything is set to 1. Now you have all these nodes. Let me number the other nodes also. Okay. So my next level of nodes, if you see, when you take out, now I'll extract the queue. First come, first serve. So I will extract 1 from the queue. When I extract 1 from the queue, I add all the adjacent vertices of 1 that are not that have not yet been discovered. So if anything has been discovered, that is in the queue right now, so it would have turned gray. So adjacent to, let's say if there was an edge here as well, 2 is already in the queue, that means 2 is already gray, it will not be enqueued, it will enqueue A after this. Okay, and the distance of A will be distance of 1 plus 1, so distance of A is 2. Then 2 will be dequeued, and adjacent vertex B is enqueued, the distance of B is set to 1 plus 1, 2. Then similarly 3 is dequeued, C is enqueued, that's the only one connected. Then 4 is dequeued, and D and E, these are the adjacent vertices, so they are enqueued, and their distance is set to 2. Then 5, when you take out 5, F goes in, distance of 2. When you take out 6, G goes in, distance of 2. For example, you had something here. This is X. Okay. Now when you DQ B, sorry, A first, there is no adjacent vertex to A, so end, then you DQ B. There's nothing to NQ because there's no vertex next to B. Similarly for C, D, when you DQ E, you have to NQ X. So X goes in the Q, and the distance is 3. Then you take out F and G, and then in the end you'll take out X also, so the Q will be empty. So if you remember, we said DFS works with stacks by way of the recursive calls. You're pushing, as you traverse a vertex, you push it into the stack. And once you have to come back to a particular vertex, you take it out, and you check its adjacency list, and then accordingly you will push or pop in the stack. So here it's a queue because you want to go in order in sequence. So once you are at source S, you want to visit all its adjacent vertices first before going to the next level. So all the adjacent vertices are kept in the queue so that you can visit them first in the same order in which they were enqueued. So once you're done with that first level of adjacent vertices, by the time you are dequeuing them and examining their adjacency list, you are enqueuing them as well in the queue. So you will first finish with all the adjacent vertices of S, and then you will finish with all the adjacent vertices of the next node that you dequeued. So if you see here, okay, so if you see here in this example, you start at you enqueue the source node in the queue. The distance of source node is 0. Once you dequeue it, you take out S, you put W and R, which are the adjacent vertices, and their distance is distance of S plus 1. So this is your basically level 1, those nodes that are at a distance of 1 edge from the source. So then once you we had W, we are dequeuing W first. It's first in the queue. So when you dequeue W, you put its adjacent vertex T and X there, and their distance is distance of W plus 1, so that is 2. So W is gone from the queue. Then you take out R and you put in V at the end with a distance of 2. So now you are at those, your queue contains all those nodes that are at a distance of 2 from the source node. So now we'll start examining them for their adjacent vertices. So you take out T and U gets updated. Then you take out X and Y gets updated. Then you take out V. V doesn't have any adjacent vertex, so nothing gets added to the queue. Now you will take out U. There is no adjacent vertex, so nothing gets added, and you take out Y, and you are done with your breadth first search. So the distances, if you want to know what the breadth first tree looks like, you have to imagine that all these nodes are like balls that are connected with threads to each other. So if you pick up this source node in your hand, all the other nodes, they will hang downwards, so they look like this. So if you pick up S in your hand, if all of them are balls connected with some string, this is how they will, sorry, this is R, and this is V, then this is W, T, U, W, X, Y. So you see sources at level 0, level 1, level 2, and level 3. This is your breadth first search tree after you traverse the graph. This is, the graph does not change. There are 2 more edges here, but for the tree that will not count. This is basically, this gives you the tree representation of the breadth first. This will tell you the paths from S to all the other vertices at which are at different levels from S, different distances, 1 edge, 2 edge, and 3 edge in this case. So if you see here what we are doing in breadth first search, for every vertex you first initialize, you color it white, you initialize its distance to infinity, you initialize its parent to nil. Parent is important because you need to know from which edges you traversed to get to a particular point. You color as gray, put its distance as 0, parent is nil, and the queue is empty. You enqueue S in the queue. Okay, then you start your loop. In the loop, you continue looping till your queue is empty. So first you dequeue S, and for every adjacent vertex in of S, you, if they are white, only then you will enqueue them. If they are gray, means they might already have been enqueued by some other path. Then if they are white, you will color them gray. Okay, you will increment their distance by 1. You will set their parent to U, which in this case first loop is S. Then you will enqueue this node, because we are going to add all the adjacent nodes of S to the queue. You will enqueue that, and once you are done doing enqueue of all the adjacent vertices of S, or in this case U, when you come out of the loop, because if all your adjacent vertices turn gray, then you are done. In case of breadth first search, you are done, and you uh, you mark or color that node as black. Okay, so simple. If you look at this, you have a for loop that does a DQ and NQ for all the vertices. So if you're talking of DQ or NQ in a simple linked list, it's a one-step operation to add one element to the queue, and a one-step operation to take it out. So you are adding every vertex and you're taking it out as well. So you can say it's twice V, NQ plus DQ operation, which we will just consider as V. And this is your this part. So it's no, sorry, it's not exactly twice V. So let's, okay, let's clear this up here. So your initialization takes, you initialize all the vertices with white color and their distances as infinity. So after initialization, every vertex is enqueued and dequeued at most once, and each operation takes a one-step operation. So again the time taken is V. O of B, so 2V, OV, same thing. The adjacency list of each vertex is scanned at most once. So you are, if you have S connected to, let's say, 10 adjacent vertices, all these adjacent vertices are in a linked list. So it's something like this. How does an adjacency list look like? You have this S, A, B. S is connected to A, S is connected to B. So if S has, let's say, 3 outgoing edges, the adjacency list of S will be this. Okay, A is connected to B, B is connected, and A is also connected to C, B is connected to C. C, if it's a directed graph, then you'll have only one way edges. If it's a undirected, then A is also connected to S. If S is connected to A is also connected to S. So that way you will have two E edges in your adjacency list. If it's directed, you'll just have E number of edges. So total time will be V plus scanning all these adjacency lists, because to add a adjacent vertex to your queue, you need to know how many adjacent vertices are there. How will you get them? You go to the adjacency list and scan it and see. It's a linked list. So if there are 5 edges going out of 5, this will be 5. If there are 2 edges going out of A, this will be 2. If there are 2 edges going B, so you add all of them. And if it's, I think we discussed it like last time, if it is a, let's do an example that will make it clear. So you have this graph. So when I try to make a adjacency list for this, A is connected to B, and A is connected to C, A is connected to D, B is connected to C, B is connected to D, C is connected to D only, D, let's say D is connected to A. So how many edges are we talking about? 1, 2, 3, 4, 5, 6, 7. And how many edges we have? 1, 2, 3, 4, 5, 6, 7. So equal number of edges and equal number of edges in the linked list of the adjacency list. So now if I make it a simple graph without any directions, so my adjacency list will look like this. A is connected to B and C and D. B is connected to A, C and D. C is connected to B, A and D. D is connected to A, C and B. So 12, you have 1, 2, 3, 4, 5, 6 edges. So 6 into 2. If it's not a directed graph, you will have 2e number of basically edges to scan in the adjacency list. If it's a directed graph, it will be equal to the number of edges, which was the previous case. So when we go back to the analysis of breadth first search, you are, even if it is 2e, if it's a not a directional directed graph, we usually omit this 2 because we are using O of v plus e. So you sum up this OV time, and if you take it as 2v, you take this one as 1e or 2e. Overall, it is O of v plus e. You drop the constants, and this is your runtime. So it's the same for DFS and it's the same for BFS. The only difference being DFS requires recursion, which can be like the disadvantage of recursion is it has to use system stack. Um, Nowadays, you don't have that problem of running out of stack space and other things. So it's not a disadvantage in that sense. Okay. So this is your breadth first search. This is almost what we will do under general graph algorithms. What we are going to do next is these were you can use breadth first search also for finding the shortest path in terms of the number of edges you need to traverse to go to a particular node. So once you form that breadth first tree, it will tell you how far a node is. So you can do a shortest path if you're not considering weights, shortest path in terms of number of edges using BFS. You can find the shortest path. Okay, so you'll know which nodes are at distance 1, distance 2, and distance 3. Okay, Dijkstra's you can find single source shortest path. Bellman Ford you will find single source shortest path for negative edges as well. Dijkstra's will not. Bellman Ford will also tell you whether there's a negative cycle or not. So the next algo that we are discussing, it is for all pairs shortest path. You want to find the shortest path between all the pairs of vertices in your graph. So Floyd-Warshall algorithm is a dynamic programming algorithm. So if you just recall what a dynamic programming algorithm is, you uh, you construct the solution in a bottom-up fashion. So you find the smallest subproblem, and using that, you find the larger problem, and then go on till you get to the actual problem. So what is your actual problem? It is finding the shortest path from, let's say, I to j. So the shortest path between any two vertices can have either no vertex in between, or it can have any number of vertices in between. Okay, so if you see in the picture here, the shortest path will consist of some short, if there is an intermediate vertex between I and j in the shortest path, then, like I said, unless and until the distance between I to k is the shortest and from k to j is the shortest, this overall uh, path will not be the shortest, right? It's intuitive. So shortest path from A to B and B to C, it has to be, both the paths have to be shortest for the overall path to be shortest than any other available path. So when we say there's a path from I to k and then there's a path from k to j, okay, so how they define the problem is that if you are given, let's say, 10 vertices, so I take a pair of vertices I and j. Okay, I have to find shortest path for all pairs. So for example, I'm taking I and j. So I want to find the shortest path from I and j. Let me see first what is the distance between I and j. Let's say it's something 10. Okay. What if I go between from I and j through one? Okay. Through one intermediate vertex. So does that give me a better solution or a better distance? Yes or no? If it does, then I'll update my solution and say the shortest path between I and j is not the direct one, it is through a particular vertex 1. Then what happens when I have two vertices? So I check all the possibilities of going from between I and j through one or two. I'll get to the example. I think that will be better that way. Okay. Okay. Without going there, let me just. Okay. Look at this graph. Don't look at whatever is written on the left side. So if I am trying to find the shortest distance between 4 and 3, okay, 4 and 3, the actual distance between the edge 4 and 3 is minus 5. Okay, what if I introduce one intermediate vertex, which is node number 1? So when I go from 4 to 1 and then 1 to 3, the distance is 10. This is not less than my existing minus 5. So this is not the shortest path, obviously, right? So I will ignore that. Let's see between 4 and 2. If you see 4 and 2, there is no direct outgoing edge between 4 and 2. So initially, it is infinity, the distance between 4 and 2, when I am not considering any intermediate edge. Okay, there is no edge, but there is an edge. Now, if I'm considering 1 as my intermediate, so this and this gives me a distance of 5, which is okay, better than infinity, so I will update it. Okay, then let's go for distance between 4 and 5. Again, 4 and 5 does not have a direct edge. So I'll go from 4 to 1 when I have an intermediate vertex, and from 1 to 2 and I have a distance of minus 2. Okay, this is the case when I look at the graph. I want to find the shortest path from 4 to all other vertices in the graph. So I found for 3 it is minus 5. In the first round it was minus 5. Initially it was infinity. Distance from 4 to 1, let's say it was 2. 4 to 5, initially it was infinity because there is no direct edge. When I introduced intermediate vertex 1 through 1, if I am trying to go to 2, 3, 4, and 5, through 1 this did not change. Through 1 going to 5, this changed to minus 2. Through 1 going to 2 changed to 5. So this was my first. Uh, this was when I introduced one vertex in the path between 4 and 1, 4 and 5, 4 and 2, and 4 and 3. Now, if I introduce a, these are the distances you see here, minus 5, 5, and 2 for all these vertices. Now, if I introduce two intermediate vertices, now this is my second round. So this is my bottom to up approach. First, I go with the direct edge, whether it exists or not, and my distance depends on the direct edge. Wait if it is there, and my distance is infinity if the direct edge is not there. Then I introduced one intermediate vertex and saw and checked if the paths through this intermediate vertex gives me a better result. So in for some cases it did give me, I updated. Now if I introduce two intermediate vertices, so when I am looking for the path between 4 and 3, initially I could only hop to 1 and then 3. Now I have two intermediate vertices, 1 and 2. So if I go from 4 to 1 and 1 to 2 and 2 to 3, okay, whether taking this path gives me a better result. My initial distance was this -5. So if I take this route, I'm getting 9, which is not a good way. So that's why your 4 3 has not changed here. Now what about 4 2? 4 2 again, it was 5, it is still 5. And what about 4 5? So what about 4 5? Again 4 5 is still -2, so no change when I introduce one more intermediate vertex. Okay, now if I introduce a third intermediate vertex, so from 4 to 2, okay, now I can go from 4. What are the different paths available to me to go from 4 to 2? One is that I can go from 4 to 1 and 1 to 2, which gives me a distance of 5. Now because 3 is also there, I can go 4 to 3 and 3 to 2. So which is -5 plus 4, which is -1. So introducing an alternative path by adding one more vertex is giving me a better result. So I update it to -1. 4 to 3 is still -5 is the smallest distance, and 4 to 5 still -2 is the smallest distance. Okay, so next, okay, this is done for 4. So this is what we do before going into this. So what we do is we create a we want to find one we find want to find the shortest distance between all pairs, and obviously the distance would mean the actual path, all pairs shortest path problem. This is an all pairs shortest path, so we want to find the path and as well as the shortest distance. So what we do is we initialize two matrices. Here, this and this. This is your simple adjacency matrix for the graph. It has infinity if there is no edge, and it has the weight of the edge if there is an edge between your nodes. So this is 1 2 3 4 5, which I think you can just assume this is your adjacent. This is the graph. Basically this is your graph. And what is this? This is the predecessor matrix. So if there is an edge between, if you see here, 3 and 2, okay, so initially, wait, go back to 3 8. Yeah, this is your 1 1 2 3 4 5. So if you look at this first row, there are three edges going from 1 to 2, 1 to 3, and 1 to 5. So the parent of 2 3 and 5 is 1, because the edge is going from 1. So this is where we will update once we find a shorter path, let's say from 1 to 3 through some other vertex. We will update it. Okay, so this is nothing. D0 or just pi 0 is your initial graph with no modifications, just what you have. Okay, now what we are going to do, okay, so what are we trying to do? Just read what is written at the end. I just read it out for you. Path P, whatever P, is the shortest path from vertex I to j, and k is the highest numbered
intermediate vertex of path P. So path P1, the portion of the path from vertex I to K, has all intermediate vertices in the set 1, 2 to k minus 1. And P2 path may you'll have all the vertices from k plus 1 to j. So we are actually taking up the vertices in order. So hamara, when I say k is an intermediate vertex between in the shortest path from I to j, जो path P1 है, it will have all intermediate vertices in the set from 1 to k minus 1. So we'll just see that in a while. So what we do, we denote dij, just forget the k, as the shortest path from I to j with intermediate vertices, obviously excluding I and j, from the set 1 to k. So we take, just like in the example we said, we are trying to see the shortest path from 4 to all other nodes. So initially dij, what I was actually calculating when I started off, it was d, let's say 4 1. If you saw there d 4 2, initially it was 0 with no intermediate vertex. This would mean the if there is an edge between the cost of the edge 4 1, if at all it is there, cost of the edge 4 2, when it is the zeroth iteration, which would mean when there are zero intermediate vertices. Once you say there is one intermediate vertex, so k is 1. So you are talking of the set 1 to up to k, right? If k is 1, so this is your intermediate set, only the vertex 1. Okay. Intermediate vertex of a simple path is any vertex of P other than Vi or Vj. So that's clear. So what is Dij is equal to the weight of the edge between I and j with no intermediate vertices. And when we introduce an intermediate vertex, we will, as and when we introduce, we will, that will be our next iteration. So we'll see that here in the next slide. So what is our recursive? We are again, this is a recursive solution, because what we are doing is we are saying the distance between I and j. Here, if you look at this, let's read it out. The distance between I and j with k intermediate vertices is minimum of the distance between I and j with k minus 1 intermediate vertices. So initially when I start with 0 intermediate vertices, then I start with 1 intermediate vertex, then I start with 2. So when I put 2 intermediate vertices and I check the paths through them, if my solution with one intermediate vertex had a minimum value, I will obviously go with that. So it is minimum of either what you already had in the previous iteration or in the previous case with k minus 1 intermediate vertices, or minimum of that, or if you introduce this in between, this k. So now you're saying I had gone I from I to j with k minus 1 intermediate vertices and I had some distance d1. Now I am going from I to j through another, there are two paths. So I check what is the distance between I to k, the shortest path, plus the distance between k to j. In the obviously the previous iteration, because that are my bottom up calculations. If going through k is a better option, if that distance d2, you find the minimum of the two. If this is the case, then everything stays like it was, and if this is the case, then you have to update the parents obviously as well as the distance. So, and remember this k intermediate vertices, when I say, if you see here the result, when you add all the intermediate vertices, you get dij with n intermediate vertices. That is what we want. We want the distance between every pair of vertices with all other vertices in as intermediate vertices. Okay, so we solve the problem step by step. We solve d0, that is your here, this d0 is the original graph with distances between every pair with no intermediate vertex. When you add 1 as an intermediate vertex, it changes to d1. Okay, so dk contains the shortest path weight with all the intermediate vertices from the set 1 to k, and when it's n, it is from 1 to n. So if you have understood this, what I explained in the beginning, let me know. If you want me to repeat this, then we'll repeat, because this is uh, the easiest way to explain, because when you move ahead, it's very difficult to explain it in paper as well. You have a matrix like this getting updated with every. So do you want me to explain this once more, or is it clear? You can raise your hand, or okay. Right, assuming it is all clear, we'll just move ahead with this. So okay, let's go here. So how does the algo work? You initialize d0 with the original weights. Okay, for you have to do n iterations, so your k will go from 1 to n. Okay, you want to find all pairs 1 2, and you want to find all pairs. So for that, you obviously you have two for loops for I and j to get all the pairs. Obviously d11 is 0. There's no edge between 1 and 1, so that is all also taken care of. We'll see what the initial conditions are, and then we do this very simple. You have to, for first iteration, initially it will be dij0 is already initialized, so dij with one intermediate vertex will be minimum of dij of 0. So either whatever initial weight was there, dij of uh, 1 minus 1 is 0. Sorry, dik plus dkj 0. Okay. So your first, with one intermediate vertex, you check if it was better off with two intermediate, with no intermediate vertex, or it is better off by uh, using k as an intermediate vertex. So for all the pairs here, your k, for when k is 1, it will check this for all the pairs. When k is 2, it will check this for all the pairs. K is 3, and so on. It will check for all the pairs. Okay, and your this matrix will get updated. So if you see complexity very clearly, there are 3 for loops. All the for loops are running n number of times, which is the number of vertices in your uh, graph. So complexity is n cube, not a very good complexity. So there are improvements on Floyd-Warhsall as well. Okay, so let's just skip this one. You don't need. So similarly, how do you update the parent? If you are going with, initially your parent is nil if there is no um, edge between the vertices, and if there is an edge with some weight, the parent of j is I. And how will you update the parent? You have to see what you selected out of the min of 2. If you remember, in knapsack we had min of the pick and to pick the vertex or drop the vertex, right? So we used to put a 1 or 0 in our table separately to see whether we pick the item or drop the item. So similarly, between the two values in the min, we have
dij 0 or dik plus dkj. So whichever, if you've selected this, that means your parent is going to be uh, k is the intermediate vertex, so the parent will be uh, chosen from the, you're actually constructing a path, so you're not just putting k, you are putting the parent of ij in the sorry, minimum this one. So parent is the same as it was in the previous, and if you've changed the path, the parent is the parent of kj. So kj is the shortest path, usme jo parent tha, that will go here. Okay, so how do you print? I'll tell you with an example. You are printing using the parent matrix, which I'll just explain to you. So if it's very difficult to explain unless you do it on paper yourself and update this matrix. So using this example above where we found how the values get updated for the pair 4 to 1, we can do that for, you can do that for some other pair and see how it gets updated. So this is your final result. Okay, if you uh, let me take a, okay, so what is the shortest path from 1 to 2 eventually in the graph? That is marked with the red here. So you're going from 1 to 5, 5 to 4, 4 to 3, and 3 to 2. So how is it represented in the matrix here? So this is 1, 1, 2, 3, 4, 5. So how do you go from 1 to 2? This tells you you want to go from 1 to 2. Okay. So it tells you 3 is an intermediate vertex. Okay. Okay, how do you go from 1 to 3? It tells you 4 is an intermediate vertex. And how do you go from 1 to 4? It tells you when you go from 1 to 4, 5 comes in between. And how do you go from 1 to 5? The parent of 5 is 1. That means, so 15432 is the, so if you look at here in this graph, 15432 is the path from this. So once you update the shortest path, you are updating the parent matrix as well, and you can use, just like in case of knapsack, we go to the last value and we see whether it's a 1 or a 0. If it's 1 or 0, accordingly we subtract the weight of that item, then we go to the previous row and see whether that value is 0 or 1. It is the same. So we go, if we are finding the path from 1 to 2, we see what is the parent of 2 in the path that has already been calculated here. So that is 3. The parent of 3 from, what is the path from 1 to 3? So the path from 1 to 3 has 4, path from 1 to 4 has 5, and path from 1 to 1 is 1. Okay, so all you have to do is, okay, this is what will print your shortest path. If you see what it does, if it is nil, there is no path. Else it says print, it calls it recursively. So if you're looking for a path from I to j, okay, so you will, that is equivalent to finding the path from I to pi of ij, which is the value of ij. So the parent of whatever j that we pick from the pi matrix. So you are calling that recursively till you get. So if sorry, it was 1, we had to find 1 to 2. Pi of 1 2 was 3. So that means we have to call shortest path of 1 to 3 now. That is what we did. And 1 to 3 we found 4. Pi of 1 3 was 4. Then we would call pi of 1 4. Then pi of 1 4 was 5. We would call pi of 1 5. And that is 1. Pi of 1 1 is obviously it is when I is equal to j, then you just print I. So you would print 1, and when you would come back from the previous recursive calls, it will print j, which is 5, then 4, then 3, then 2. So 1, 2, 3, 4. It will print it in order 1, 5, 4, 3, 2. Okay. So you can just take this problem and update it, and how you don't want to do, you can do it graphically also, but better is to use this function. Okay, it's very easy to write. Even if you want to write a small C program for this, you just have to enter a matrix with these values and then just write this program, and that print one, it will give you the answer. But to understand it, you should actually do the original one with so do this one. You have to see what was the previous value and what is the new value if you go through the intermediate vertex. Now, you might not always be able to go through the intermediate vertex. For example, uh, if I tell you go to 3 from 4 using 2 as an intermediate vertex, if that is the first one, if 1 was not there, there is no edge from 4 to 2. Obviously, for that, you will get a infinity value, so it will never be selected. So that is taken care of in the algorithm. Okay, so this is your Floyd-Warshall algorithm. Runtime complexity is very high. In it's n cube, and normally, if your graph is sparse, then even then it will make the similar number of iterations on the matrix. There's a alternative algorithm which we'll discuss in the next class, which uses again in this the assumption is there is no negative weight cycle. So an alternative algorithm called Johnson's algorithm, it uses uh, Bellman-Ford, and it uses Dijkstra's algorithm to find the shortest path between all pairs. Okay, so uh, we'll talk about that in the next class. I think it's already 1 o'clock. So some people have a couple of questions. Let's finish this graph algorithm, and if you still get some time before midterm, we can do some revision kind of for the syllabus. Before I go, I want to share or show you, where did that go? Mm, let me see just a second. Okay, it's here. Here. So this is your syllabus. I'll mail it to you. I think there might be some additions based on what we have done this semester. This is what we covered just now. This is a dynamic program, and this is also a graph algorithm. We have completed almost till here. Almost, maybe there are a couple more things that I have not mentioned in this. What is left after this are these topics. So based on the syllabus, it looks like pretty much most of it is going to be in the minors. Uh, I will try to. So algorithms, divide and conquer. First one is important because that's the basic mathematics. This one you've already done, merge sort, quick sort. It's just a matter of understanding and writing the reconciliation and solving it. This is from where the main thing starts, dynamic and greedy. So what we can do is we can do dynamic and greedy and all the greedy graph algorithms. Okay. Uh, mhm. Okay. I'll frame a midterm syllabus थोड़ा सा इसे कम करके so that there's something left for majors also. If there's only
a few topics left for me. Just okay. I'll just update it by evening. I'll mail it to you. The final syllabus. If you have any suggestions, you can give me now. आप तो बोलोगे कुछ रखो ही नहीं मैम सिर्फ फर्स्ट यूनिट रखो there are a couple of things people have asked me. Mm, I will just try to take it up in the next class after we finish the Johnson's algorithm. Okay, some recurrence relations. There are 10 marks for your class assessment, and what I was thinking that we should have a random question and answer session in one of the classes too from now onwards so that I can give you some assessment marks out of those 10 marks if you people are ready for that. So your silence means you're all ready for that. Okay. Aman, have you taken the attendance? इतने obedient बच्चे हो आप लोग.
Yes, ma'am.
Have you taken? Okay. There are a couple
Yes,
of
sir.
questions pending. I will answer them hopefully in the next class after we finish Johnson's. I'll take only one class, depending on. I have two classes on Wednesday and Thursday. I'll just take one class this week to finish off graphs, and if your exams are next week, that will be it for classes before midterm. So let me just find out whether the date sheet, etc., has come. Uh, I'll let you know. Okay. All right. Thank you. Thank you very much.
Okay, ma'am. Thank you, ma'am.